A hidden Earth? Imagine this. Somewhere out there in the vastness of the cosmos, a rocky planet orbits its star at just the right distance for life. It's Earth-sized. It may have water. It could even host life. And yet, we can't see it. Why? Because it's shrouded in cosmic dust. This is the hidden reality of exozodiacal dust, or exozodi, a mysterious veil of particles orbiting distant stars, silently concealing potentially habitable planets from even our most advanced instruments. Why NASA is focusing on exozodi? A recently submitted NASA white paper, spearheaded by Dr. Miles Curry at NASA's Goddard Space Flight Center, has spotlighted a profound cosmic dilemma: the possibility that exozodiacal dust, commonly known as exozodi, isn't just an observational nuisance, but perhaps the very factor obscuring our ability to detect Earth-like exoplanets. This research doesn't just raise questions, it refocuses the trajectory of how we seek life in the universe. The white paper outlines how exozodi accumulates specifically within the habitable zones, HZ, of stars, the coveted regions where temperatures are just right for liquid water to exist. These habitable zones are the prime hunting grounds in the search for extraterrestrial life. Yet, ironically, this same region is often choked with fine particles of cosmic dust that scatter and reflect light in unpredictable ways. The presence of this dust creates a luminous veil that dramatically complicates our efforts to observe planets directly. Advanced imaging techniques such as direct imaging and spectroscopy are particularly vulnerable. The scattered light from the dust acts like cosmic static, masking the signals we need to identify planetary atmospheres and surface conditions. What makes this issue even more pressing is that many of our future missions and telescope designs are centered around imaging planets in these exact habitable zones. The realization that exozodi could severely inhibit our capabilities means that our best chance at discovering an Earth twin may currently be hidden in plain sight, shrouded by a fog of stardust. This insight is pushing NASA and the broader scientific community to reevaluate how we model, detect, and ultimately see through these dusty obstacles. Dust or atmosphere? Dr. Curry explains that the biggest challenge astronomers face is the problem of misinterpretation, a fundamental confusion rooted in the similarity between the ways light interacts with dust and with planetary atmospheres. When we observe starlight filtering through a distant planetary system, both cosmic dust and atmospheric gases can bend, scatter, and reflect this light in eerily similar patterns. This overlapping behavior makes it incredibly difficult to distinguish whether a detected signal is the result of a true atmospheric signature, such as the presence of oxygen, water vapor, or methane, or simply light being distorted by the surrounding exozodiacal dust. This confusion isn't just a minor inconvenience, it carries massive scientific consequences. In the worst-case scenario, we could be staring directly at a potentially habitable world, one that breathes, that hosts liquid water, that maybe even supports life, and fail to recognize it. The planet's true identity could be completely masked by the cosmic dust surrounding it, leading scientists to dismiss the observation as a false positive or background interference. This means that entire Earth-like worlds might go undetected, not because they are too distant or too dim, but simply because their light has been scattered in a way that mimics lifeless debris. It's a sobering reminder that in the vast theater of space, even a small veil of dust can cast a shadow large enough to hide another Earth. Where does exozodi come from? Despite more than a decade of dedicated investigation, the true origins of exozodiacal dust, exozodi, continue to elude scientists. One prevailing theory suggests that it could be the aftermath of ancient, large-scale collisions between planetary bodies, events that pulverize rock into fine particulate matter. Another possibility is that this dust is not born in the habitable zone at all, but instead drifts inward from the colder, more distant reaches of the star system, pulled along by gravitational interactions or the subtle push of stellar radiation. What makes this even more intriguing is the dust's physical nature. The individual grains are tiny, measuring just 1 to 100 micrometers across, comparable in size to a human hair. But in massive numbers, they coalesce into luminous, sprawling rings that stretch across entire solar systems. These rings are not merely decorative. They act like a cosmic fog, scattering starlight and making it incredibly difficult for astronomers to isolate the faint signals of exoplanets. Their sheer presence can overwhelm delicate observations, essentially cloaking entire worlds in light and shadow. In this sense, the origin of exozodi isn't just a curiosity. It's a critical piece of the puzzle in our quest to understand planet formation, system dynamics, and the potential for life elsewhere in the galaxy. Cracking the code on how and why this dust forms could lead to better models for predicting its behavior and, eventually, more effective strategies for seeing through it to the planets beyond. Modeling the dusty cosmos. In 2013, NASA took a significant step in addressing the exozodi mystery by launching the Collisional Exozodi Simulation Catalog, an ambitious, data-driven tool designed to model how exozodiacal dust behaves across a range of planetary system environments. This simulation suite allows scientists to manipulate key parameters, such as a planet's mass, its orbital distance from the host star, and the size and tilt of the surrounding dust cloud, to create a variety of hypothetical system configurations. From there, researchers can predict how the dust would scatter light, behave dynamically, and appear in both optical and infrared wavelengths. This is invaluable for planning future observations and interpreting faint signals that might otherwise be misread or overlooked. These simulations are particularly important because, despite their potential ubiquity, direct detections of exozodiacal dust are still quite rare. Real-world observational confirmations remain frustratingly limited. To date, only a select few systems, such as 51 Ophiuchi, Fomalhaut, Tau Ceti, and Vega, have provided compelling, observable evidence of exozodi. Each of these systems offers a unique case study. For instance, 51 Ophiuchi is believed to represent a young planetary system still undergoing violent collisional processes, while Fomalhaut's intricate rings have captivated astronomers for decades, especially after recent imaging by the James Webb Space Telescope revealed multiple concentric dust structures. Tau Ceti, on the other hand, boasts an unusually dense dust disk, reportedly 10 times dustier than our solar system, raising intriguing questions about its dynamic history and potential for hosting terrestrial planets. Meanwhile, Vega's disk is estimated to contain several times the mass of our asteroid belt, suggesting a highly active or recently disturbed environment. Together, these systems form the tip of the iceberg in our understanding of exozodi. Each detection is a vital puzzle piece, helping scientists refine their models and improve observational strategies. Yet they also serve as a reminder of how much more remains hidden and how tools like NASA's simulation catalog are crucial in preparing us to uncover it. A universe full of dust. Interestingly, the white paper refrains from naming specific exoplanetary systems as research targets, and that omission is quite telling. According to Dr. Curry, the reason is both simple and profound. Exozodiacal dust might be present in every stellar system across the galaxy. It's not just a rare anomaly confined to a few distant stars. Instead, it could be a universal phenomenon, an ever-present veil cloaking countless worlds from view. The challenge isn't necessarily in knowing where to look, but rather in developing the technology and observational techniques to see what's already there. The hosts hunt for observable signatures of terrestrial systems. Survey has made some of the best progress in detecting and quantifying exozodi so far, providing a foundational dataset for understanding dust distributions. However, even this ambitious project has only begun to scratch the surface. Our detection capabilities are limited by current sensitivity thresholds, and many systems likely contain low levels of exozodi that fall below the radar of existing instruments. This uncertainty underscores the need for more comprehensive surveys and specialized observatories. As we expand our toolkit with next-generation telescopes and refined dust models, we may find that the universe is teeming with dusty environments we've simply been unable to perceive. Until now. The road ahead. Looking forward, the path is clear. The future of exoplanet exploration depends on targeted investments in science, engineering, and innovation. We need more robust funding initiatives to support long-term research, more advanced computational models to simulate dust dynamics, and significantly better telescopes capable of resolving the faintest signals buried beneath cosmic haze. This includes both next-generation ground-based observatories like the Extremely Large Telescope, ELT, and spaceborne missions like the proposed Habitable Worlds Observatory, HWO, which promise unprecedented sensitivity to faint light and subtle planetary signatures. But this isn't just about seeing more, it's about seeing better. The dusty veils of exozodi may seem like barriers, but they are in fact windows into the story of planetary systems. Dust is not just an obstacle to be removed, it's a cosmic narrator. Each grain carries within it the legacy of ancient collisions, the remnants of asteroid belts, or the whispers of icy bodies migrating inward. Studying it can reveal how planets are born, how their orbits shift over time, and even how conditions for life might arise. As Dr. Curry puts it, one astronomer's noise is another's signal. What seems like interference may actually hold the key to unlocking mysteries of habitability, planet formation, and cosmic evolution. So yes, the path ahead is complex and dusty, but the rewards may redefine our understanding of the universe. Uncovering the unknown. By investing in exozodi research, we're not just clearing the way for better planet hunting, we're embarking on a larger journey of cosmic discovery. Each particle of dust we study, each simulation we run, and each telescope we calibrate takes us one step closer to revealing the hidden dynamics of distant star systems. Exozodiacal dust, though a nuisance for observation, is an archive of planetary history. Traces of collisions, migrations, and the chaotic dance of celestial bodies. Understanding this dust means understanding the environments in which planets evolve. It helps us separate the background noise from the precious signals of possible life-bearing worlds. With every dusty veil we pull back, we not only gain a clearer view of potential Earth-like exoplanets, we gain insight into how planets like ours form, survive, and possibly host life. This pursuit isn't just for scientists with high-powered telescopes. It's for everyone who has ever looked up at the night sky and wondered what lies beyond. The search for other Earths is a search for context, for perspective, and for connection in a vast and ancient universe. So, as we peer deeper into the universe, the race is on to clear the dust, not just to find planets, but to unlock the stories of the stars themselves. Somewhere, perhaps just a few dozen light years away, another blue world could be waiting to be seen. As always, keep doing science and keep looking up.